Hello everyone, welcome to the next Saturday session for the NPTEL course Novel Technologies for Food Processing and Shelf Life Extension. So in this week we'll be discussing syllabus related to week 5. So we'll begin with the first question. In a freeze dryer, a product having thickness of 10 millimeter is dried. The product surface temperature and sublimation temperature is 50 degrees Celsius and minus 20 degrees Celsius respectively. The thermal conductivity of the dry part of the product is 0.03 watt per meter Kelvin. Determine the drying time in hours and assume that the heat of sublimation is 2840 kJ per kg and density of ice as 917 kg per meter cube and porosity of the product as 0.8. So any clue how to move forward with this question? Any clue how to find out the drying time in for a freeze drying process? This has been discussed in one of the lectures before. Okay, we'll look at how to solve this problem. So we have the length or thickness of the product as 10 millimeters. We have the surface temperature Ts as 50 degrees Celsius and sublimation temperature, that is at the sublimation front. So as and when your product is getting freeze dried, you will have certain part of the product that will now become dry because all the ice is sublimed, and there will be certain part of the product that is still frozen. So the sublimation front is where your dry product ends and your frozen product starts. So that is your sublimation temperature, sublimation front or sublimation temperature. So this is where your frozen product starts, and this is the surface, that is where your dried product would probably be there. So this is the surface temperature, which is 50 degrees Celsius, and sublimation temperature or sublimation front temperature is minus 20 degrees Celsius. You have your thermal conductivity as 0.03 watt per meter Kelvin. The heat of sublimation is given as 2840 kilojoule per kg, density as 917 kg per meter cube, and porosity as 0.8. So when you have porosity given, the how you'll calculate the freeze drying time is that Td, which is your freeze drying time, is equal to L square rho into delta Hs into phi divided by 8k Ts minus Ti. So here L stands for your thickness of your product, rho stands for the density of the ice, delta Hs stands for the sublimation heat, phi stands for the porosity of the product, K stands for thermal conductivity, Ts for the surface temperature, and Ti as a sublimation front temperature. Okay, so we have all the parameters here already in the question, given in the question. So all we have to do is just substitute all the values in the equation, and you can get the Td values or the drying time. So proceeding with it, I'm substituting L as 0.01 in meters. So 10 millimeter is converted into meters, which is 0.01 square into 917 kg per meter cube into 2840 kilojoule per kg. So kilojoule I'm converting into joules. So I'm multiplying by 1000. So 2840 into 1000 into 0.8, which is the porosity of the product. So certain products have a lot of porosity through which your ice will sublime and turn into vapor. So porosity of the product is actually important in determining the drying time. So as you can see here, the drying time is directly so into porosity divided by 8 into 0.03, which is your thermal conductivity, into 50 minus 20. So 50 is your surface temperature, minus 20 is your sublimation front temperature. So when you substitute all the values, you get TD as 12,401.33 seconds. And since the question is asked for the drying time in hours, you convert it into hours by dividing it by 3600 and you get 3.44 hours. The answer is option B. Is this clear? So if you guys have any doubts or if you know the answer, you can either unmute yourself or you can post it in the group chat. We can discuss that particular problem again if you want as well. Okay, so moving on to question 2. Oatmeal with a moisture content of 12% wet basis is being extruded through a metering zone of an extruder with the dimensions of the channel as width 4 cm, height 2.5 cm, length 45 cm. The rheological properties of the extrudate can be estimated by a viscosity of 67,000 pascal second and a density of 1250 kg per meter cube. The wall velocity is estimated to be 0.4 meter per second. If the pressure drop maintained is 2500 kilopascals, estimate the flow rate of the extrudate in the metering zone. So before we proceed with this, do you guys know what an extrusion process is? So any clue what an extrusion process is? You can either unmute yourself or you can post it in the in-call messages. So an extrusion process is when you want to get a desired shape of your food product. So like say how you have pastas of different shapes and sizes, those all come with a specific shape. So this is done by a process known as extrusion, where you'll feed in the dough or your raw material, and because of high pressure and temperature it will get extended, the shape will change, and at the end of the process there will be something known as a die or a kind of a hole that will determine the shape of the food that you are extruding. So if you look at this is how an extrusion equipment looks like, where in this feeder is where you'll pass in your raw material, and you see here a very big screw. So this screw will keep on rotating, and because of this rotation you'll have a lot of friction that is generated, and on top of that there will be heaters as well. Here it is not shown, but there will be heating elements as well. Because of the friction and the heating element, the temperature of your food product will increase, and on top of that you're screwing the food continuously. So because of that there will be an increased pressure as well. So with the help of high pressure and temperature, you will change the texture and the properties of the food material, and the food material will pass from the feed to the exit. So this is where you will have a die or a particular hole which will give a shape to your food product. So based on the shape of the die, your shape of your food product will also change. So this is how your extrusion process looks like. So when you mean there are three different regions to your extrusion process. First is the feed, where you will feed in your raw materials through the feeding zone. The second zone is the compression zone, where your pressure and temperature will start increasing because of the screwing nature. And last is your metering zone. That is where your texturization and all will take place. That is a change in texture, change in shape, and everything will take place in the metering zone. So here the metering zones dimensions are given. The channel is width is 4 centimeter, height is 2.5, and the length is 45 centimeters. The extruder's dimension is given, and then the rheological properties of the extrudate. Extrudate means the food product that is coming out of this die is known as the extrudate. So the rheological properties of the extrudate is given, and wall velocity is given. So wall velocity is that here you can see as the screw starts twisting, there will be zero velocity at this end, that is at the wall of the barrel there will be zero velocity, but as your screw is moving you will have velocity just at the surface of the screw. So this surface of the screw has a velocity known as the wall velocity, whereas the velocity at the barrel will be equal to 0. Is this clear? What is a wall velocity? So with this given, we need to find out the flow rate of the extrudate in the metering zone. I'm sorry, I'm not feeling well, so excuse me. So the given is that the width is given as 4 centimeter, height as 2.5 centimeter, length as 45 centimeter. Now the viscosity is given as 67,000 pascal second, density is 1250, and the wall velocity is 0.5 meter per second. And the difference in pressure is given as 2500 kilopascals. So we need to find out what is the flow rate of the extrudate. That is, the extrudate will come from the feed and all will move through the extrusion equipment towards the die. So there will be a flow rate of the extrudate coming out from the metering zone. So the flow rate through the extruder can be given by delta P W H cube divided by 12 mu L, where V dot is the volumetric flow rate, delta P is the pressure maintained in the extruder, W is the width of the extruder, H is the height of the extruder, mu is the viscosity, and L is the length. Just a minute. So generally, if wall velocity is not given, you assume this term to be 0, and this is how you calculate the volumetric flow rate. But if the wall velocity is given, this is the formula that you use. So U wall is the wall velocity, H and W are the height and the width of the extruder. So using this formula, we will calculate what is the volumetric flow rate of the extrudate coming out from the metering zone. So this is a direct substitution formula again. We have all the parameters given in the question. So proceeding with this, delta P can be given as 2500 kilopascals. So we are converting this into pascals. So 2500 into 10 power 3 pascals. Width is given as 0.04 meters. So centimeters we are converting it into meters. So 0.04. Height as 0.025. The height cube divided by 12 into viscosity, which is 67,000 pascal second, and length is 45 centimeter, which is 0.45, plus U wall is 0.4 meter per second, H is 0.025, width is again 0.04 divided by 2. So this particular term is due to the volumetric flow rate due to the pressure. So since you have a certain pressure that causes the flow of the liquid, this first term is contributed by the pressure or the pressure flow. The second term is contributed by the wall flow. So here in this case, since you have a wall flow given, you can consider wall flow as well. If nothing is given, you directly consider the flow due to pressure. So the first term is due to the pressure flow, the second term is due to the wall flow. We are substituting the values, and the term corresponding to the pressure flow, that is the volumetric flow rate due to the pressure, is 4.31 into 10 power minus 6 meter cube per second, and the volumetric flow rate due to the wall velocity is 2 into 10 power minus 4 meter cube per second. So basically I just simplified these two terms, and this is what I got. So the volumetric flow rate comes out to be 2.0431 into 10 power minus 4 meter cube per second. So the answer is option A. Any doubt in this question? So these formulas are not given in the lecture videos, not completely, but they are a part of your assignment questions that have come up in last year's assignments as well. So these might come up in your exam or in your future assignments. So that is why we are discussing these numericals. So any doubts? Okay, so if you guys have any doubts, you can ask me to pause or repeat the question again. Moving on to question 3. The rate of heat transfer in freeze drying depends on the dash and dash of the ice layer. So you have different properties given here: thickness, thermal conductivity, temperature, pressure, and thermal diffusivity. So there are different combinations of the parameters given here. So what do you think majorly influences the rate of heat transfer in freeze drying? Any clue what are the two most important parameters for determining the rate of heat transfer? Okay, so before we go into the parameters, what are the different ways in which you can transfer heat in a freeze drying process? Any clue? Okay, so there are actually three different ways in which you can transfer heat. I am discussing only two here. So one of the way is to transfer heat through a frozen layer. So in these figures, the dark thick black arrows shows the heat transfer, and the lighter arrows show the mass transfer. So heat transfer is because you're supplying heat for sublimation of the ice. So ice sublimes and then transfers and then converts into water vapor, and that water vapor uh, and that water vapor is then transferred from the food product into the air, into the into the air, which is then taken up by the freeze drying equipment. So that we'll discuss a bit later. So the darker arrow shows the heat transfer and the lighter arrow shows the mass transfer. So as you can see here, there are two different ways of heat transfer. There's a third one also. I'll explain that as well. So here the shaded area consists of the frozen layer and the non-shaded area consists of the dry layer. So as you can see here, you can transfer heat through the frozen layer or you can transfer heat through the dry layer. So there are two different ways. So the third way is to have, instead of a heat transfer, you can have microwaves that generate heat. So you subject the food to a microwave, and that microwave will then generate heat and then result in mass transfer or sublimation process. So in both the cases where you're transferring heat through the frozen layer or the dried layer, it is the thickness and the thermal conductivity of the food that's most important. In case of microwave generation, it's a completely different principle. So you do not require thermal conductivity or the thickness coming into picture. Since here in this case we're talking about conduction here, conduction mode of heat transfer. For conduction mode of heat transfer, both the thickness and the thermal conductivity plays a very important role, and hence these two are the most major parameters that are involved in the rate of heat transfer. Whereas in the third case of heat transfer, where you are having microwave generation, it does not depend on thickness or thermal conductivity. Hope this is clear. So the answer is option A. So moving on to question 4. In case of radiation freeze drying, the source of heating is dash with the speed of vapor movement as dash meter per second. So this is another mode of freeze drying instead of just conduction. So any clue what the answer is? So any clue what the answer is? Yeah, so infrared radiation will be the source. So apart from microwave generation, you have also infrared radiation that can also be a source of heating. So infrared radiation, and you ensure that you give only that much radiation so that the speed of the vapor, that is your vapor that is being sublimed, sorry, ice being sublimed into vapor, has a flow rate of only 1 meter per second. So this is to ensure that there is uniform drying taking place. So if you are uh, the speed of the vapor is extremely fast, it might lead to non-uniform drying, where certain regions of the food will dry more and certain regions will remain wet. So ensure an optimal range of vapor movement, and this is ensured by the amount of infrared radiation that you give inside the food. So infrared radiation from radiant heaters are used to heat shallow layers of food on flat trays, where the air movement should be 1 meter per second for uniform drying to take place. So the answer is option A. Moving on to question 5. Which of the following statements is false? A. Multi-batch freeze dryers are the type of industrial freeze dryers. B. Tunnel freeze dryers are a type of pilot scale freeze dryers. C. Continuous freeze dryers are a type of industrial freeze dryers. And D. Tunnel freeze dryers are a type of industrial freeze dryers. So what is the difference between pilot scale and industrial scale freeze dryers? So in a pilot scale freeze dryer, you are dealing with very small quantities of food that need to be freeze dried. Whereas in case of industrial freeze dryers, as the name suggests, you're looking at very, very large quantities. So according to the quantity or the kind of food that you're trying to freeze dry, you have different kinds of freeze dryers. So there are three of them actually. There is one is a multi-batch freeze dryer, where you'll have a huge equipment and you can have multiple batches of the food kept inside, and you'll have a freeze drying process will happen as a batch process. The second is a continuous freeze dryer, where your product will be continuously going in and coming out, and there's a particular time known as the residence time inside the freeze dryer. So according to your kind of food product that you're dealing with, your residence time will vary. So if you're dealing with a product that can be easily freeze dried, so your residence time inside your continuous freeze dryer will be less. If you're dealing with a product that needs a lot of time to undergo this sublimation, then your residence time will be more. But your product will continuously be coming in and going out, and according to the kind of product that you're dealing with, there are different kinds of continuous freeze dryers as well. And the third type is the tunnel freeze dryers. So this is how a tunnel freeze dryer looks like. So you have an inlet and you have trolleys here. So these trolleys will have trays or your food products kept in these trolleys, and this trolley is moved from one point to another point. And as it moves from one point to another point, there is vacuum generated and there's a heating process also that takes place. And because of this vacuum and heating, your ice will get sublimed into water vapor as the trolley moves from one end to the other end. And once the freeze drying process completes, then this part of the gate is opened and then you can take your trolley out. So this is known as a tunnel freeze dryer. So it basically looks like a large tunnel through which you will send a trolley of food inside and you'll freeze dry it and take it out from the other end. So this is how your tunnel freeze dryer looks like. So all these three processes, both the multi-batch, the tunnel freeze dryers and the continuous freeze dryers, all of them come under industrial freeze dryers. That is, you will be dealing with a large amount of food samples and not like a pilot scale which requires very small amounts of foods. So all these three processes is where you will take in large amount of food samples and freeze dry it either continuously or in batch modes. So hope this is clear. So these three types are the major, the first category of industrial freeze dryers, and these can be further classified into multiple other freeze dryers that we're not dealing with here right now, and this is actually mentioned in the second lecture of this week. So the answer is option B. So B statement is false. It's not a pilot scale freeze dryer, it's an industrial scale freeze dryer. So going to question 6. What is the range of product capacity for a pilot or a laboratory scale freeze dryer? Any clue what the answer is? Okay, so this is how a pilot scale or laboratory scale freeze dryer looks like. So here you can see it's a very small equipment, and you can keep only 2 to 20 kgs of the food product inside the pilot scale or laboratory scale freeze dryer. So the moment you want to freeze dry more than 20 kgs, that is when you will move on to the industrial freeze dryers. So the answer is option D. It can hold up from 2 to 20 kgs of the frozen product. Moving to question 7. Make proper combination of the components of a pilot scale freeze dryer with its function. So column A consists of all the components of a freeze dryer, that is the freezing fluid system, heating circuit, vacuum system and the chamber. And column B consists of the functions, different functions that each of the components can do. First is defrosting the condenser, second is the product freezing, third is place for drying, and fourth is evacuating air. So any clue what are the combinations? So we'll go one by one. What do you think is the role of the freezing fluid system? Okay, so as the name suggests, the freezing fluid system is used for product freezing. So freezing fluid system will basically be kind of a coolant kind of a fluid that will freeze the product. But despite this freezing fluid system, it is most probably preferred that you already pre-freeze the product and then place it inside the freeze dryer. But still the freezing fluid system will ensure that your product is completely frozen at all times. So the freezing fluid system is important for product freezing. So the freezing fluid system can be sent to the heat exchanger of the condenser or to the refrigeration coils for product freezing. So the second unit is the heating circuit. So the heating circuit is used for defrosting the condenser. The heating circuit, or it contains the silicon oil as your heating fluid, is used for heating the plate and defrosting the condenser. So the heating the plate is necessary to provide that energy for sublimation. So the heating circuit will help in sublimation of the ice, and second thing, it will help in defrosting the condenser. So what happens is that once your ice gets converted into water vapor, it will then move to the condenser. The water vapor will move to the condenser where it will turn back into ice. So the condenser will take, so the water vapor that is evaporated from the food product will go to the condenser and it will get accumulated there. So if you don't remove the accumulation in the condenser, your freeze drying efficiency will reduce. So it is necessary to defrost your condenser time and again so that the efficiency of freeze drying is not affected. So the heating circuit will provide the heat of sublimation and it will also defrost the condenser so that the efficiency of your process remains the same throughout. The third is the vacuum system. So vacuum system is necessary for evacuating the air. Any clue why do we need to evacuate air in the freeze drying equipment? Why can't we run it at atmospheric pressure? So why do we go for freezing and then a vacuum system? So if you guys remember the pressure versus temperature, yeah, it is to remove the moisture, but why can't we do it at atmospheric pressure is because that if you remember the phase diagram of water, only at lower temperatures, that is lower than the critical temperature and lower than the critical pressure, you can have a solid gas transition. Otherwise, if you do it at atmospheric pressure, what will happen is your ice will turn into liquid first and then you will have to sit and evaporate the liquid. So that is not what happens in a freeze dryer. In a freeze dryer, you directly sublime the ice into water vapor. So this sublimation process can happen only at lower pressures or in vacuum. If it happens in atmospheric pressure, your ice will turn into liquid or water first and then you will have to sit and evaporate, which is not preferred, because then you will have to give too much heat to the system. That is, you will have to go above 100 degrees to evaporate the liquefied water. So the process of solid to liquid is not preferred in a freeze dryer. You look for solid to gas transition. So this solid to gas transition can only occur at pressures below the atmospheric pressure, that is at when it is under vacuum. That is why a vacuum system is necessary for evacuating air, and that is how you will maintain sublimation process instead of liquefying process or condensing process. So hope this is clear as to why we require a vacuum system. So the freezing is necessary to maintain that ice does not move into liquid, and again vacuum will also maintain the same thing. Why vacuum will also ensure that ice does not move to liquid, ice will directly go to gas phase. And fourth is the chamber. The chamber is where you'll keep your product. So chamber is where you keep your product for freeze drying. And chamber, as you see on the previous slide, is like kind of a bell jar where you'll maintain very low pressures and very low temperatures, and this is where the freeze drying occurs. So in the previous slide, this is the chamber. So this is where you'll keep your product. This is the chamber that will maintain a low pressure and a low temperature for freeze drying processes. So in each of these plates is where you will keep your food. So these four components are the most important parts of a pilot scale freeze dryer. If you look at industrial scale freeze dryers, there's a lot more stuff that comes in. You'll have pumps and everything, but in this case it is much more simpler equipment that you're dealing with in case of a pilot scale freeze dryer. The answer is option C. The freezing fluid system is for product freezing, heating circuit is for defrosting the condenser, vacuum system is for evacuating the air, and chamber is a place for drying. So hope this is clear. Any doubts regarding the function of any of the components? Okay, moving to question 8. Which of the following is not a freeze dehydration related process? So A is freeze concentration, B is liquefaction, C sublimation, and D condensation. So there are different processes that very closely relate with the freeze drying processes. So which one is not related to the freeze drying process? So we'll go one by one. Do you know what is a freeze concentration first? Okay, so in a freeze concentration, what you do is you freeze the product completely, and then you start subliming it, and or basically you freeze the product, and then you'll have ice crystals forming in your product. So when you remove these ice crystals, just the ice, not the solute. So if you remove these ice crystals, the concentration of your solute will increase, because now you have removed water in the form of ice. So what you have left is only a concentrated product. So this is known as freeze concentration, where you'll freeze the sample, you'll help the ice grow, and then you'll remove the ice, and what you have left is a concentrated product. So this is known as freeze concentration. So often this is done prior to freeze drying process, so that the amount of ice then you have to sublime will be lesser. So your freeze drying time will also reduce. So if you already remove the ice as much as possible before the freeze drying process, the amount of time that you require for the actual freeze drying process will become lesser. So freeze concentration is often a step that occurs before the freeze drying process to remove all extra ice or extra water molecules that can be easily removed. So freeze concentration is one of the process that is related to freeze dehydration. And as I explained in the previous slide, sublimation is also a part of freeze dehydration, where in the actual freeze drying process, you will sublime the ice directly to water vapor, and then you will remove that water vapor. And then condensation is also important, as I explained earlier. You will condense all the water vapor that you are taking out in the condenser, so that the water vapor does not go back and mix with the product. That is also important. So if your water vapor starts touching the frozen product again, it can again turn back into ice. That is, it can again deposit as ice. So if you don't remove the water vapor continuously, if it remains in the chamber itself, it can come in contact with the frozen product again and turn back into ice. That is not something that you want. So it is necessary to continuously remove the water vapor, and that is done by the help of condensation. So your condenser will condense all the water vapor that is coming out and keep it separately instead of coming in contact with the product. So these three are the processes that are involved in freeze dehydration. So processes related to freeze drying consist of pre-freezing, that is you are freezing the product already for like few hours. So the more better it is frozen, the better will be your freeze drying process. If you have partially frozen product, it will often result in froths or bubble formation, and this bubble formation will damage your product. So you need to make sure that your product is completely frozen before you go forward with freeze drying. So pre-freezing is a very important process. Then is freeze concentration, where you remove all the extra ice. Condensing is a process where your water vapor will be condensed and kept separately. And then defrosting is what we discussed in the previous slide, where you have to defrost whatever has been deposited on the condenser to ensure that your efficiency remains the same. So, but sublimation is also a part of freeze drying because you are converting your ice directly from solid to gas. So, from all these four options that are given, liquefaction is the only thing that is not involved in freeze dehydration. In fact, you have to prevent liquefaction as much as possible, because once your solid turns to liquid, it might result in bubble formation and it might require a lot more energy. Then you'll have to give the heat of evaporation to evaporate all the liquid, and that is a lot more energy. So if you're dealing with very thermal sensitive products, and if it so turns out that your ice changes into liquid, then it will be very difficult to remove that liquid, because now you'll have to heat the liquid to 100 degrees and then remove it. And if you're dealing with a thermal sensitive product, then it will damage your product as well. So liquefaction is something that you have to completely prevent in a freeze drying process. So the odd one out in these options is liquefaction. So the answer is option B. So any doubt in this? Any process that needs to be repeated again? Okay, then moving on to question 9. Which of the following is the correct sequence for the process of freeze concentration? So you have four different steps here. There is crystal nucleation, there is crystal growth, there is separation of ice, and then there is concentration. These are the four major steps involved in freeze concentration. So as I explained in the previous slide, can you figure out which one is the correct flow chart for the process of freeze concentration? So what is involved in freeze concentration? First you freeze your product, and because of the freezing of the product, you will have ice crystals forming. So the first step of any crystal formation is called as crystal nucleation, where your molecules will come close together and it will start the process of crystal formation. So crystal nucleation will come when your molecules start coming together. So crystal nucleation is the first step for any crystallization process. So first step is the crystal nucleation. Then your crystals will start growing. That is, the size of your ice crystals will start becoming bigger and bigger. So your crystal growth is your second step. So once you have a significant chunk of your crystal growth that is big enough size, then you can separate all the ice, which is your third step. And because of this separation of ice, you will have only your solute left out behind, and hence it will have a much more higher concentration than your initial food product. So first step is crystal nucleation. Second step is the crystal growth. Third step is separation of ice, and fourth step is concentration. So the answer is option A. Is this process clear? First is the starting of crystal formation, then the growing of the crystals to a particular size so that it is big enough to be removed by the separation, and then you have concentration. That is, once you remove the ice crystals, what you have left is a concentrated product. So the answer is option A. Hope this is clear. So moving on to question 10. If any question needs to be repeated, kindly let me know. Which of the following affects the temperature of collapse in a freeze drying process? So you have moisture content, pore size, bulk density, solute concentration, and true density. So which of these are important for determining the temperature of collapse? And before that, do you guys know what is collapse in a freeze drying process? So as in a freeze drying process, you supply heat for sublimation. So at a particular temperature, what happens is that all your water molecules start subliming from ice to water vapor, and at a certain temperature, what will happen is that your food product will become so weak because of all sublimation that it can no longer hold its structure. So basically, it will collapse into a certain powder or some kind of a weak structure. So this collapse happens in a freeze drying process, and we need to often ensure that we maintain the temperature below the temperature of collapse so that you don't weaken the structure so much. So you need to make sure in a freeze drying process, you need to make sure that the structure of your product remains the same. You don't want the structure to start collapsing in your food product because that will not be preferable to the consumers. So you need to make sure that your fruit product does not collapse because of too much of sublimation, and this collapse is highly dependent upon two properties of your food. One is the moisture content, and second is your solute concentration. So both the moisture content and your solute concentration highly determines the viscosity of your product, and this viscosity of the product will indirectly affect your temperature of collapse as well. So what happens is that as and when you supply temperature for the sublimation process, there will be change in the bulk density because the product is getting heated to a certain temperature. So because of this change in bulk density, what happens is that your structure will become very weak, and this will result in a collapse. And this happens when the mobility of the concentrate phase increases. So you're giving supplying more and more heat, so your concentrate, that is your other molecules, will also gain mobility. So it is not just your ice that gains your mobility or gains velocity, it is also your concentrate or your main food product or your solute. So that also starts gaining mobility, and because of this gain in mobility, what happens is that the structure will collapse, and the temperature at which this collapse occurs is known as the collapse temperature. And this is a function of your moisture content and the solutes, because both of these together can also determine the viscosity of the product, that is important for the determination of temperature of collapse. So moisture content and the solute concentration are two major parameters that affect the temperature of collapse in a freeze drying process. So the answer is option C. So when you're dealing with a freeze drying process, you can't keep on heating as per you like it. You have to always ensure that the temperature of your food product is always lesser than that of the temperature of collapse. This is to ensure that your structure remains intact. Hope this is clear. What's the collapse temperature? Any doubts? Okay. So moving on to question 11. Which of the following are the correct sequential steps for processing of freeze-dried instant coffee? So you have multiple steps here. You have extraction, you have filtration, you have reserving aroma, you have aromatization, and then you have freeze-drying process. So any clue which process comes first? Okay, so the first step in any ways is that you have ground coffee beans, and you need to extract your coffee and your aroma from that coffee ground beans. So the first step of any coffee manufacturing process is the extraction. So first step is the extraction, and then what is your interest is the filtrate. So you need to filter all the extracted product, and hence filtration comes as the second step. So after a okay. So what happens is that first, when you're dealing with coffee manufacturing, you will have large amounts of coffee beans that needs to be ground and then extracted and then filtered. But then the filtrate that you have is very very dilute in nature, and you need to concentrate it to a certain extent. So this is where your freeze drying process comes into picture. But then before the freeze drying process, there are certain steps that occur. The answer is not option A. I'll tell you why. Because so yeah, after the filtration, you have a very dilute sample that you're dealing with. So what often people do is that what in a freeze drying process, often your aroma is lost, because that often those are also volatile substances. All the aroma that you get in coffee are also sometimes volatile in nature, and that might also sublime along with your ice. So that is not something you want. You want to preserve the aroma that is there in your coffee product. So what happens is the third step is you extract all the aroma giving compounds separately. So the third step is reserving of aroma. So you take out all your aroma giving compounds, and then you do a freeze drying process. In the freeze drying process, you will get a powdered coffee that is much more concentrated than your initial extract or a filtrate that you got. So the fourth step is the freeze drying process, where you concentrate the product and you'll turn it into powder. And after the powder, now you have to bring back the aroma in the coffee. That is when you will take whatever aroma containing compounds that you had reserved separately before, and after the freeze drying process, you will subject the coffee powder to those compounds again. So you'll mix those compounds with the coffee powder, and this process is known as aromatization. So your aromatization will be the last step. So first step is the extraction, then is the filtration, where you'll get a dilute coffee filtrate. Then you'll take out all your aroma giving compounds, because those will get affected in the freeze drying. So you want to preserve that aroma that is most preferred in the coffee. So you are separating all the aroma giving compounds. Then you are converting the coffee into a concentrated powder. After you get the powder, you are bringing back the aroma again. So then it enters the dehydration phase, and this is done by the freeze drying process. And then after that, the volatile aromas that were recovered in the earlier step are then sprayed onto the dry coffee particles. And finally, the instant coffee powder is packaged in a moisture proof packaging material. So the answer is option D. That is, you take out the aroma, then you convert it into powder, and then bring back the aroma. So the answer is option D. Hope this is clear. So this is the sequential process for a freeze dried instant coffee manufacturing process. So moving to question 12. What is the total suspended solids of the coffee extract after the extraction step during the instant coffee manufacturing process? So you have the extraction step, and then comes the filtration step. So what is the total amount of suspended solids that you have in the extraction step? So after the extraction step in the instant coffee manufacturing process. Any clue? Okay, so what happens in the extraction process is that you have multiple trays or multiple columns of ground coffee beans, and you pass softened water through it. When we mean softened water, it's not hard water, or it does not have all those salts and something. So it is softened water that you pass through multiple columns of coffee beans, and once you pass through that, and you maintain a certain temperature, so that all your coffee compounds and flavors are then transferred from the coffee beans to the water. This is how your extraction takes place at a certain temperature, and when you pass water through multiple columns of coffee beans. And once you get the extract, this extract is then cooled down. That is, initially it was 100 degrees Celsius, then you cool it down to about 5 degrees Celsius because you want to do a freeze drying process later. So you will cool it down with the help of a heat exchanger, and at the end of this cycle you have around 20 to 30% of your coffee solids. Then you will freeze it and then subject it to freeze drying process so that you can increase this amount of coffee extract that you have. So in the first step of extraction, you have only 20 to 30% of your solids. And after your freeze drying process, you can increase it to how much ever is your coffee, according to whether it's a strong coffee or a mild coffee. According to that, you can increase the concentration of your coffee extract by the help of freeze drying process. It is a multi-purpose process where you can both change it into powder as well as you can concentrate it. So the first step after the extraction, you have 20 to 30% of your coffee extracts. So the answer is option B. And the process in which extraction takes place is you pass hot water through multiple columns of ground coffee beans, and this will extract all your suspended solids. Okay. Moving to question 13. The zone where the amorphizing and the texturization occurs in an extruder is, you have A, feeding zone, B, cooking zone, C, kneading zone, and D, all of the above. So we discussed what are the different zones in one of the initial slides. So there are other names for these zones as well. So any clue which area does the amorphizing and the texturization takes place? Yeah, the answer is cooking zone. So there are three types of zones in the extrusion. First is the feeding zone, where you will feed all your raw materials introduced into the barrel. So that feeding zone. Second is the kneading zone, where you will have an increase in temperature as well as pressure. That is, the compression of the material will take place in the kneading zone. So as the name suggests, you basically knead your uh, raw materials that you supply with the help of high pressure and temperature. And the last one is the cooking zone. It is also known as the meteorizing zone that we discussed in the previous slides. So the cooking zone is where the increase in the temperature and pressure will lead to shear rates, and that is, this temperature and pressure will give you the texture and the amorphous nature of the product. And at the end of the cooking zone is where you will have your dye, which will give it a particular shape for the food. So the major zone where your screw, or the screw that is present inside the extruder, will play a very major role is the cooking zone, where you will start to extend your product. It will undergo a lot of shear rates, and this will result in changing of your texture of your food product. So the answer is option B. Moving to question 14. What do you mean by compression ratio in a food extrusion process? A, flight length by outside diameter. B, feed depth by metering depth. C, velocity of the extrudate after expansion divided by velocity of the extrudate inside the die. And D, cross-sectional area of the extrudate divided by cross-sectional area of the die. So any clue what is the compression ratio? There are certain parameters that you need to maintain to ensure proper food extrusion, and all of these options given below are one of the parameters that are involved. So yeah, feed depth divided by metering depth is the compression ratio in food extrusion. So A is the L by D ratio. So if you look at, this is how your screw looks like. This entire length, or the length of the screw, or also known as the flight of the screw. So this is the L, this is the D. So L by D is what, this is known as the L by D ratio. That is, the flight length divided by outside diameter is known as the L by D ratio. The feed depth divided by metering depth. So here, this is the feed zone, this is the metering zone. As you remember, the first starting will be the feed zone, and the ending will be your metering zone. So this, the distance between your barrel, that is the outside wall, to your screw, this will be a certain height, and this will be a certain height. So it is not necessary that your height will be constant throughout the extrusion process. Sometimes you will have a decreasing height and sometimes you will have an increasing height. So in this case, sorry. So in this case here you can see your height is decreasing here. So you have a lot of height in your feeding zone. You have a reduced height in the metering zone. So because of this reduced height, this will ensure a lot of shear rates and higher compression and then texturization of your food. So it is often seen that your metering zone will have a lesser height, whereas your feed zone will have a larger height. So this ratio, that is your height at the metering zone between your barrel and your screw and your height in the feed zone, the ratio of these two corresponds to the compression ratio. So the higher the compression ratio, more is the compression of your food product that you're dealing with. That is, the more smaller your height is in the metering zone, so more compression that you're giving to your food product. So C is the longitudinal expansion index. So what you mean by extrudate is the food product that is coming out of your die. So the velocity of the extrudate after expansion. So you pass in all your food materials inside the extrusion process. It goes through the different zones and it comes out through a product, the equipment component known as the die. So once it comes out through the die, suddenly there is no pressure, too much compression pressure. So all of a sudden your food will start expanding once it comes out of the die, because there is nothing to give it that compression force anymore. So the moment your food comes out of the die, there will be an expansion that is happening. So the velocity of the extrudate after the expansion and the velocity inside the die, that is this region, inside the die and after the die, is known as the longitudinal expansion index. That is how fast it expands is the longitudinal expansion index. And D is the cross-sectional area of the extrudate divided by cross-sectional area of the die. So whatever comes out, because of this expansion, you will often have a difference in the cross-sectional area of your food product. So the cross-sectional area of the food that comes out after the die divided by the cross-sectional area of the die will give you what is the sectional expansion index. So all these four parameters are very important, and feed depth by metering depth corresponds to the compression ratio. So the answer is option B. So any doubts in any of the parameters, or what is an expansion? Okay, so moving on to question 15. What are the general types of material flow in the extruder barrel? A is the drag flow, B pressure flow, C leakage flow, and D all of the above. So what is the answer for this question? Okay, so when you pass in food through the extruder, there are multiple kinds of flow that help it to flow from the feeding zone to the metering zone. So if this is the screw that you are dealing with and it is rotating in an anti-clockwise direction, here you can see you have QP in the same direction of the rotation, QD, sorry, it's given in the opposite direction. Okay, so QD in one direction, QP in the other direction, and you have something known as QL here. Forget about QA, because QA is something that we are not dealing with in the lectures that are given here. So here there are three different kinds of flow. So one is the drag flow, which is mentioned by QD. The other one is the pressure flow, that is QP. Third one is QL. So the drag flow is the flow of the material inside the barrel due to action of dragging. So since your screw is continuously rotating, this screw will drag the fluid or the food particles that are very close by to the screw. So basically the rotation of the screw will drag the food particles closer to it, and this represents the drag flow. The second one is the pressure flow, that is in the reverse flow of the drag. So whichever direction the screw goes in, the screw rotates, in the same direction it will be your drag flow, and then the opposite direction will be your pressure flow. And then there is a third kind of flow known as the leakage flow. So what happens is, if you remember, there will be a die at the end of the extrusion process, and the die's diameter is very smaller when compared to your entire equipment. So the moment you're dealing with a very small opening, there'll be too much pressure accumulation at that small opening. So because of that very high pressure that is accumulated at the end or at the die, what happens is that there'll be backflow that is often happening. So this backflow is what is known as the leakage flow. That is, instead of the liquid going in this direction, because of very high pressures at the end of the extruder, your liquid will start flowing in the opposite direction. So this is known as the leakage flow. So actually there's something also known as the axial flow, where your uh, liquid flows in the this direction, but that is not quite that is not something that we're dealing with here right now. So here in this case, all drag flow, pressure flow and the leakage flow together will contribute to the net flow of your food product from your feeding zone to the metering zone. So the answer is option D. All of these flows are involved in flowing your food product from the feeding zone to the metering zone. QD is in the direction of rotation, QP is in the opposite direction of the rotation, and QL is because of the backflow because of very high pressures at the die. So hope this is clear. So there are three different flows involved in the extrusion. So when you're asked to calculate what is the volumetric flow rate in an extrusion process, you have to calculate QD minus QP minus QL. So that will be your net flow towards your die. So hope this is clear. So the answer is all of the above. That is drag flow, pressure flow as well as leakage flow. So moving to question 16. In the below given figure, what is the order of the size of the die? So you have 4 different dies here: die 1, die 2, die 3 and die 4. And you have delta P, that is the pressure required, the pressure that is maintained inside the extrusion process. And m dot is the mass flow rate of the extruded product, that is the flow rate that is coming out of the die. So, and you have 4 different dies. So which one do you think is the larger die and which one do you think is the smaller die? Yeah, die 1 is larger because here you can see here the pressure that is required to maintain a good mass flow rate is very less. So when you have a large opening, you do not require much pressure to push your product through the hole. But if you have a very small opening, you'll require a lot of pressure to push the food product through the hole. So the amount of pressure that is required is inversely proportional to the size of your die. So in this case, since die 1 requires the lowest pressure, then die 2, then die 3 and then die 4, this is the size, that is die 1 is larger, followed by die 2, then die 3 and then die 4. So die 1 represents the lowest resistance, which is why your delta P is also very low, whereas die 4 being small is a very restrictive die. So the amount of pressure required to push something through the die is larger. So when is the pressure required almost zero? So there are two different conditions. There are two extremes. Either when you do not require much pressure at all to extrude the food product, and second is when you require a lot of pressure or maximum pressure that the equipment can handle to extrude the food product. So there are two extremes possible. So the first extreme is that the maximum throughput, that is everything coming out and no pressure buildup, is known as the point of open discharge. So this is where you don't have any die at all at the end. If you don't have any die, everything that you're extruding will just directly come out. So there is no pressure required at all. So this is known as the point of open discharge. So point of open discharge occurs when you don't have any die at the end and you have maximum throughput or maximum flow rate outside and there is no pressure buildup. And the other extreme is that when your die gets clogged or plugged, what happens is that even if you apply maximum pressure that the equipment can handle, there will be very less throughput or no mass flow rate. So your pressure required will be extremely high, but then the mass flow rate will be extremely low. So this happens when there's a clogging or a blockage in your extrusion process, and this is known as point of closed discharge. So the answer is option A. Die 1 is larger in size, and die 4 is the smallest in size. Moving to question 17. Which of the following is not a function of fillers used in the process of extrusion? A. Improving the flexibility of the dough. B. Reducing the swelling of starch. C. Is reducing the size of air bubbles. And D. Influencing the flow of the material. So what is the answer for this question? Yeah, so D is not a function of fillers. So in an extrusion process, apart from your raw materials, you often add other additives called as fillers. So these fillers are often protein fractions of oilseeds or cereal grains. So this is added to improve the flexibility of the dough. It reduces the swelling of starch, and it reduces the size of the air bubbles that are present that happen after the expansion of the extrudates. That is, after you pass your food product through the die, since there is no more pressure to compress it, there will be an expansion process happening. And because of this expansion process, you will have air bubbles coming inside your food product. So this is how your ready to eat products will all have air, will be very porous in nature. It will have a lot of air pockets as well. So this is because of all those air bubbles. So you need a particular concentration of the fillers to ensure that you can reduce the size of the air bubbles, so that they are very tiny ones instead of large ones. So based on the concentration of the fillers, each of these can be one of the roles performed by the fillers. So if you have too much hard fillers, then you will end up getting a very tough food. Whereas if you have too much soft fillers, you will have a very tender food product coming out of your extrusion process. So based on the kind of fillers and the amount or concentration of the fillers that you are adding, it will have different kinds of roles. So one is the improving the flexibility of the dough. Second is the reducing the swelling of the starch. And C is the reducing the size of the air bubbles, whereas it does not influence the flow of the material. That is not the role of fillers. So the answer is option D. Okay, moving to question 18. Which among the following plant protein provides the best gelling properties? A. Wheat gluten, B. Soy protein isolate, C. Pea protein isolate, and D. Mycoproteins. So any clue why we are dealing with proteins for gelling properties? Why are proteins preferred for gelling properties? Why not any other carbohydrates or any other kind of um, macromolecule? So why we prefer proteins for gelling property is that when you denature the proteins, either in the presence of different pH or temperature, basically when you unfold your protein molecule, it will unfold into a chain, and these denatured chains often have a tendency to come close together because of aggregation, because of coagulation, and it can often form a fibrous like structure or a gel like structure. So denatured proteins have a property of forming gel like properties, and that is why plant proteins are involved in gelling, because once you denature these proteins, these will form gel like structures or gel like mesh like structures, and these plant proteins are then used for gelling properties. So amongst these four plant proteins, wheat gluten is found to be one of the best protein for gelation properties, because they develop 3D structures and are often used as meat analogs. So when you heat your wheat gluten, they form fibrous structures, and once you change the texture slightly, you can often use it as a meat analog or substitute for meat. So wheat gluten is one of the meat analogs, and is used because it has an ability to form gel-like structures, which is kind of like the texture for that you get for meats. So this is an example, wheat gluten is an example of texturized vegetable protein that is used to form meat analogs. The answer is option A. And you often don't want mycoproteins inside your food product because often mycoproteins are considered as pathogenic in nature. That is, it can often lead to it reduces your nutritional value of your food product often, because these mycoproteins come from toxic fungus. So you do not prefer often mycoproteins in your food product, and you make sure that you do not have mycoproteins in your product. Okay, moving on to the last question. A twin screw extruder is having the speed of rotation of 9 rps. The average width of the pitch is 0.04 meters. The angle of helix is 25 degrees. The length of the screw is 1.2 meters. The screw tip diameter is 0.06 meter and the average screw height is 0.003 meters. The melt, having an average viscosity of 6 pascal second, is fed at atmospheric pressure. The pressure at the die is 1.55 megapascals. So calculate the volumetric output flow rate of the extruder. So as we had mentioned before, there are different kinds of flow involved in the extruder. One is the drag flow, second is the pressure flow, and third is the leakage flow. So here, by default, when you have angle of helix and everything given, you can calculate what is the drag flow. If angle of helix is not given, then you will have to calculate only the pressure flow that we calculated in the first, I think in the second numerical. Since angle of helix was not given, we stuck with the flow due to pressure. But since here the angle of helix and all is given, we'll also calculate what is the drag flow. But here, since nothing is mentioned about the leakage flow, we can assume that to be negligible. So given here, n, which is speed of rotation, is 9 rps, width is 0.04 meters, length is 1.2 meters, diameter is 0.06 meters, height is 0.003 meters. Your helix angle is 25 degrees, which is given as phi. Viscosity is 6 pascal second, and pressure that is maintained is 1.55 megapascals. So the net volumetric flow rate is flow rate due to the drag force minus flow rate due to pressure. Ideally, if they ask you to ensure leakage flow also, then you'll have minus flow due to leakage as well. But here, since we are not, nothing is mentioned about leakage flow, you can assume that to be negligible. So net volumetric flow rate is flow rate due to drag force minus flow rate due to pressure. So the flow rate due to drag force can be given as 0.5 pi d, which is the diameter of your screw, n, which is the rotation speed, w is the width of the pitch, h is the height, and phi is your angle of helix. So this first term gives the flow rate due to the drag force, and the second term, which we already looked in the second numerical that we discussed today, is the flow rate due to the pressure, where delta P stands for the pressure difference, W stands for width, H stands for height, mu stands for the viscosity, and L stands for the length. So we have all the parameters given for this particular sum. So 0.5 pi d we are substituting as 0.06 meters, n we are substituting in rps, which is 9, width is 0.04 meters, height is 0.003, and 5 is 25 degrees. So we have cos 25. This whole first term corresponds to the flow rate due to drag force. Second term corresponding to the pressure involves 1.55 megapascals. So you are converting megapascals into pascals. So 1.55 into 10 power 6 will be a delta P. Width is again 0.04. Height is 0.003. So h cube is 0.003 per cube, divided by 12 into 6 pascal second, which is your viscosity, and 1.2, which is your length. So this is due to drag force, this is due to pressure force. So if I simplify this, due to drag force, it is coming out to be 9.22 into 10 power minus 5 meter cube per second, and due to pressure force, it is 1.94 into 10 power minus 5 meter cube per second. So the net flow rate is 7.28 into 10 power minus 5 meter cube per second. So the answer is option B. So hope this is clear. If angle of helix is not mentioned and there is no way of finding it out, you can directly go forward with flow rate due to pressure only. But if the angle of helix is given, you need to consider the flow rate due to drag force as well. And since wall velocity is not given here, we are not including wall velocity in this particular formula as well. So based on what is given, you need to figure out what are the forces that are involved and accordingly calculate the net volumetric flow rate inside the extruder. So any doubts so far? Okay, so with this we wind up this Saturday session. If you guys have any doubts in the questions that we have discussed today, kindly let me know. We can repeat that question again.